Alright, let's continue. Okay, let me open the table of content first. Yeah, I'm not sure if you can hear that, but it is currently raining around here, so hopefully my internet connection is fine. Hopefully. Okay, we are still on chapter 20, patching smaller tables. Still on multi-level patch table. Let me open that. I feel like we need to revisit what is it called? We need to revisit the chapter 18. What is the chapter 18 again? Patching linear translate, I guess. Yeah, let me check that. Okay. Yeah, I want to understand about the division for the page and page table entry, something like that. Okay, let's say we have a test space size 16k, right? Oh, okay, I think import math 16.3 egg 4. Okay, log to 14. This is 14-bit and the bit size is 4k. Okay, bit. So 12-bit, does that mean 2 bits for the virtual base number and then 4? Oh, okay, so we got 4 from what is it called, from 2 power 14 divided by 2 power 20, I mean 12. Okay, right. Alright, so there is that. Info chapter 20. Yeah, I feel like the previous range that I try to understand is not correct, something like that. Where is it? Yeah, it is raining. I am not sure if you can hear me. Hello, Serhat. Welcome back. Currently we are on chapter 20 on section multi-level page table here, trying to understand what is it called. I think converting from linear page table to level page table, something like that, with the use of page directory here. So yeah. Yeah. I think I do. This concept atau some yang of my previous engineer interview they asked me about inverted page table. Oh, so learn this concept. Alright. Yeah. The next chapter is, or the next section is inverted page table. Okay. Right. Currently I'm still learning about the multi-level page table. The concept here. It's kind of tricky, I guess, but we will see. Where is it? I think. Wait, let me check. Okay, we have the 14-bit virtual address space, right? It is 16K here, and then 64-byte page size. 64-byte page size. Oh, okay. 64-byte page size. I think it is 6 bit, right? So we have 14 bits and also 6 bits here. I think, yes, the 6 bit from the page size here is the offset, and then the 8 bits is the virtual page number. So basically something like this: 2 power 14 and then 2 power 6 divided by 2 power 6. And if you take a look, right, it is 2 power 8. So the virtual page number is 8 bit. Yeah. The exponent is the bit value, I guess, something like that. Okay. A linear page table would have this one entries, the 256 entries, even if only a small portion of the address space is in use. Even if only a small portion of the address space is in use. Figure 20.4, page 8, present one example of such an address space. One example of such an address space. .4. Okay, this one. A 16 kilobyte address space with 64 byte page. This is the code. We start the code here. Okay. We start the heap. We start the stack. Okay. this example, virtual page 0 and 1 are for code, virtual page 4 and 5 for the heap, and virtual page 254 and 255 for the stack. Keep in mind that we start from 0, right? So the maximum is 255. The n -1 here. The rest of the bits of the address space are unused. Okay, that is how, what is it called? We get how much entry in a linear page table, right? Okay. The rest of the bits of the address space are unused. The rest of the bits of the address space are unused. Okay. To build a two-level page table for this address space, we start with one full linear page table and break it up into page size unit. Because our full table in this example has 256 entries, assume its page table entry is 4 byte. Okay, so each of these 256 entry is 4 bytes. Each of this entry information is 4 byte. Okay, and then the page table size is 1 kilobyte, something like that. 150 side multiplied by 4 byte, right? Around 1 kilobyte or kibibyte, I guess, the binary representation here. Okay, that is the table, the page table size. Given that given that we have 64 byte page, 64 byte page, the 1 kilobyte page table can be divided into 16. 1 kilobyte page table can be divided into 16. 64 byte page. Okay, so if I understand correctly, with 16 kilobyte address space and 64 byte page size, the linear page table have 256 entries, page table entries with the A, and this one is 2 power 6, I guess. Yeah, 2 power 6. And then this one is 2 power 14, if I remember correctly. Okay, 16. Okay. And this one is 2 power 8. Alright. Maybe something like this. The two level page table. size of the page table before to fight into this one 16 page. Let me try, I guess. 4 5 by 16. Yeah, I'm kind of curious, where do we get the 16 here? Oh, hello, ping pong poing. Welcome back. When I'm right, it's okay. I mean, thank you for joining the live stream, I guess. We are currently on chapter 20, learning about multi-level page table here. So yeah, trying to understand how do we, what is it called? How do we organize the multi-level page table? Maybe something like that. Okay, 1K page table. If I do something like this, it is 16. So maybe okay, wait, not that one. And 4 bytes. What is it called? 4 bytes page table entry size. So it's entry in the page table like this one. The information here have 4 bytes. Okay. With page table size, something like this. 256 multiplied by 4 multiplied by the page table entry size. Okay. And then can be divided into 16 pages. Okay, so we have the page table with 1K size, I guess. We divide the entry, I assume, into smaller pages, maybe something like that. I mean, previously, yeah, we divide the address space by the page size, right? And then get the linear page table entry 256 here, and then maybe we, but if I divide this again, it's gonna be 4. So it looks like we need to find the page table size. Okay. How do I explain this? Have 16, maybe small page table, something like that. Yeah, 16 is from 1024 divided by 64. Okay. This table with its small page table. With its small page table. Can hold 16 page table entry. Now how do we get this? The page table entry. Is it something like this? Oh, maybe. So we have the previous entry, right? 256 divided by 16. Yeah, this entry, right? This is for one big page. What is it called? This is for one big page table here. So in the one big page table we have 256 page table entry, and now we divide that into the smaller page table. We have 16 small page table from this big linear page table, and then inside those small page table we have 16 page table entry. I assume something like that, I guess. Linear page table entry, and then this one is small page table size. Oh, no, not really size, but the total. Maybe something like this. Total small page table. And this one linear page table size, I guess. For here is page size. Okay. is PTA, and this one is PTA size, page table entry size. Right. Okay. Oh, again. Alright, ping bong point. Okay. It may be total linear page table entry. Yeah, something like this. Or maybe using a row, I guess. Nah. Let's just use the bracket here to indicate the information that this one 256 is the page table entry, and for here is the page table entry size, and then this one linear page table size 64. Here is the page size. Each small page table can hold 16 PTA. In total linear page table entry divided by total small page table. Okay, maybe something like that. Alright, what we need to understand now is how to take a virtual page number and use it to index first into the page directory and then into the page of the page table. So yeah, I assume we need to divide the page virtual page number here to contain the page directory information and the virtual page number inside those small pages, I guess. Okay. Remember that it's I assume page directory here. Remember that its page directory is an array of entries. Thus all we need to figure out is how to construct the index for each from pieces of the virtual page number. How to construct the index for each page directory from pieces of the virtual page number. Okay, let's first index into the page directory. Our page table in this example is small, 256 entries. Let's first index into the page directory. Our page table in this example is small, 256 entries spread across 16 pages. The page directory needs one entry per page. The page directory needs one entry per page of the page table. One entry per page of the page table. One entry per page is the page in here means this 16 page. Oh, thus it has 16 entries. Okay. So it looks like per page of the page table is this 116 page. Okay. So instead of having, I guess, 256 page, we only have 16 page, right? For the page directory. So the page directory has 16 entries. As a result, we need 4 bits of the virtual page number to index into the directory. We use the top 4 bits of the virtual page number as follows. Okay, so the virtual page number is 8 bits, right? 8 bits, and then okay, yeah, it is 16. So 4 bit for the page directory index, I guess something like that. And the other 4, right, and the other 4 is for the actual virtual page number, maybe something like that. As a result, we need 4 bits of the virtual page number to index into the directory. We use the top 4 bits of the virtual page number as follows. This one is the page directory index, and I guess this one is the virtual page number for this page directory, or for the small table, I guess, maybe something like that. When we extract the page directory index, wait a minute. Now I wonder, where do we get this for bits of the virtual page number? Oh, this because it has 16 entries, I guess. Okay, so we need to chop off the 4 bits of the virtual page number to index into the page directory. Maybe something like that. Once we extract the page directory index, pt index for short, from the virtual page number, we can use it to find the address of the page directory entry. The pta With a simple calculation, PTA address equal page directory base plus PTA index multiplied by the size of PTA entry, the page directory entry, I mean. So its entry information, the size of its entry information, something like that. Okay, this result in our page directory, which we now examine to make further progress in our transaction. In our page directory, which we now examine to make further progress in our translation. Okay. In the page directory entry, if the page directory entry is marked invalid, we know that the access is invalid, and to raise an exception. If, however, the page directory entry is valid, we have more work to do. Specifically, we now have to fetch the page table entry from the page of the page table point to by this page directory entry. I mean, this term is kind of confusing for me, I guess. From page of the page table, I assume this is the small page table, right? Again, we have the big page table, the linear one, like this, right? We have a big page table here, but we chopping that off into a small page table, and for some reason this small page table is called page, but we also have this another term page, right? So it is kind of confusing. What page are we talking about here? I mean, I assume this is the, what is it called? This is the page size, right? And this one is the 16 in here is the 16 small page after we are chopping off the big page, the big linear page table. So yeah, my assumption for now is this is the small page table. Okay, we now have to fetch the page table entry from the small page table point to by this page directory entry, the PTA. To find this page table entry, we have to index into the portion of the page table using the remaining bits of the virtual page number. The remaining bits of the virtual page number, this one. Yeah, page table index, the small page table index, to differentiate between the linear page table and the two-level page table here. Okay, this page table index, PT index for short, can then be used to index into the base table itself, giving us the address of our base table entry, like something like this. Oh, okay. Base directory entry also have the page frame number. Okay, left shift that to get the base. I think the base for the base directory entry, and then adding the base table index. Maybe some kind of offset within those page directory entry. Okay. Note that the page frame number obtained from the page directory entry must be left shift into place before combining it with the page table index to form the address of the page table entry. Right. So this is, we can think of this as some sort of the page table entry base address, maybe something like that. And then this one is the offset into the small page table, and then I think we got the actual address after we add this offset. So we, what is it called? We are adding a few offset, maybe something like that. Okay, page directory entry plus or maybe plus offset to small page table, and then plus offset for the PTA, the page table entry. Maybe something like this. This is the base address for this page directory entry. I think similar to, not this one, or maybe in this one. Yeah, what I mean by base entry, something like a base address is something like this. For this page 1, we have the base address of 1024, and for this page 2, we have the base address of 2048, and so on until, well, page 10 or page 15 here. And that's why we need to left shift to get the, what is it? To get the base address for the small page table. How do I explain this? PTA left shift page bits, I guess. To get the base address for small page table, and then speeds. I think I'm not sure if we use arithmetic or operator here. I mean from previous script here. Is this the one? Maybe not that one. Yeah, maybe this is the one. But I don't. Oh, okay, right. I remember adding this flag. Okay. Yeah. For this one, to get the physical address, right? We are using orbit-wise operation here instead of the arithmetic operation to add the bit from the offset into the base address here, if I understand correctly. So maybe we do something like this. Stable index. Small page stable. Small page stable entry, I guess. Maybe. To get the base address. Not necessarily the base address. Wait, let me think. The base address. If this is the base address for small page table, what is this operation to? Adding an offset. Maybe to get the small piece. If we add this, we are only entering the virtual page number, right? Not the offset too. I mean, we need to also add the offset. Or maybe to get the small page table virtual page number, maybe like the index, right? So this one, the left shift is to get the page address for small page table, like where this small page table reside, and then we add that, and then with this operation we add the, what is it called, we add the page address here with the small page table virtual page number. Yeah, maybe let's call this index, I guess. Small page table index. Maybe to get the small page table, to get the small page table virtual page number. Okay. And then we're adding this again. Offset, right? I'm not sure if this assumption or this hypothesis is correct or not. To get the virtual page address, maybe something like this. That make me wonder, is this the, what is it called, the virtual address, the actual virtual address? I mean, wait, previously, right, we have this figure 20.3, right, the illustration of multi-level page table on the right here. So this is the page directory, right? And inside this page directory, this page directory entry, I assume there is some kind of smaller page table here, and each of these small page table, right, have its own page table entry. Oh, okay, right. Okay, so this is only the page table entry address, like the, I assume like the, like the here, the page table entry here, the page table entry, maybe something like that. Okay, or in this case maybe call it the virtual page number, right, the virtual page number here. So this is the page table entry for the small page. Yeah, maybe something, I'm not sure if this read from the bottom or from the top, but from this information, right, page 1 of page table, it looks like we read this from the bottom, I guess. So this is page 0, I mean this is the subpage, maybe something like that, the subpage 0 and then subpage 1, maybe that's what it is here. Page 1 of page table not allocated, and this one, page 2 of page table not allocated, is this one. So this is subpage 0, subpage 1, and then subpage 2. Another term that we can use is maybe the subpage. I mean, if we are gonna call this small page table as a page, right? Maybe we can call this subpage. Maybe there is that. Yeah, anyway, this is the base address for the page table entry for the small page table. Personally, I prefer the term small page table to make it easier to understand, but I'm not sure if that term is correct or not. Just something to keep in mind. Okay. To get the you know what? Maybe this is not. Maybe this is not the best address for small page table. Maybe this is just the address for small page table, and then the base address for the small page table is after we add this. At the small page table index. Maybe to get the small page table base address, right? Wait. Previously in the linear, what is it called? In the linear page table, right? This one is in here, is the virtual page number or the index in the page table, right? And this is the base address for the virtual page number, which means that we add this page bits, we right shift, okay, after writing the max, okay. Address for small page table, okay. Maybe the base one, I mean, should we like, let's shift this to, maybe not. I'm thinking this is some kind of life shift, I guess. Yeah, what is this shift? Let me think. Page frame number. Okay. Okay, I assume this is page directory, page register. Okay. It's the page frame number. Yeah, maybe by adding this one and this one, we get the best address for the page, I guess. And then we add the offset there. Maybe or this is also the offset. Yeah, I assume this is just the index, I guess. So let's say 201, 201, and then adding 12, let's say. This is the page frame number, maybe something like that. And then we need to get the offset to get the actual what is it called, the actual physical address. Maybe something like that. To get the small page table, maybe let's call this page address. And then from this base address we add the offset to get the actual base address. Maybe something like that. Hello, Courtney. Are you going to college? No. Where are you from? I'm from Indonesia. The actual Indonesian AI, right? I am from Indonesia. Okay, ping pong point said that I get EP now. I might fall asleep while watching your stream. Sorry, good night by the way. Don't forget to drink water and eat breakfast. No worries. No worries, ping pong point. Have a nice dream, I guess. Brutus is an AI. Yeah, I am an actual Indonesian. For better or worse. Okay, thank you. Okay. Alright. Yeah, maybe something like this. Maybe. So the page frame number from page directory, and then the 12 here is page frame number from a small page table. Yeah, maybe something like this, and then the offset. But yeah, that make me wonder, do we also need to left shift? What is the shift in this case mean? Left shift. Yeah, is this the page speed? But this is the size of the size of page table entry. Okay, so I assume we left shift this with the page speeds, like what is it, in the 64-bit 64 byte, I guess it is 6-bit, maybe something like that. So maybe this shift here is 6, and then we multiply the page table index by the page table entry, which can also be left shift 2, right? Where is it? It is 4 byte, so left shift by 2, maybe something like that. Left shift by page table entry on let's PTA bits, maybe something like that. Page table entry bits, and then the offset. I think that to the offset. Okay, maybe something like that. Maybe I'm still trying to figure this out. Okay, note that the page frame number obtained from the page directory entry must be left shift into place before combining it with the page table index to from the address of the page table entry, right? I assume this is the base address for the page table entry, similar to this one. For example, this is the base address for the page table entry 10. It is 10,240, right? So the, what is it called? In this case, the page table entry 10 have the range address 10,240 until 11,263, if I understand correctly, something like that. So this is the base address for the base table entry, and then we need to add that to the offset to know the exact address or the actual page address there. Okay, that is my understanding so far. Okay. To see if this all makes sense, we'll now fill in a multi-level base table with some actual values and translate a single virtual address. Let's begin with the page directory. Let's begin with the page directory for this example. Offset of figure 20.5. Well, you know what? Maybe let's continue this on the next session. Yeah, let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.